In this video, we're going to do two more examples just to illustrate some of the things that you can do with internal effectiveness factors. In our first example, we're going to develop the Thiele modulus and effectiveness factor for a first-order reversible reaction. Now, A can go to B, but B can also back react. The rate law for that is going to be the one shown here. We're going to assume that A and B have the same effective diffusivity in the porous pellet, right? So this problem can get a bit more complicated if A and B have different diffusivities. At all points in the pellet, the reaction stoichiometry ensures that the concentration of A and B is going to remain the same because they're only converting one into the other. That means that we can write the reaction-diffusion equation entirely in terms of either of the two components. So if we write it in terms of species A, then we get the diffusivity of species A down into the pellet, the rate at which species A is being consumed. We get the rate at which species A is being generated through consumption of species B. This is just CB written using this conservation of the total amount of A and B. All right, now this reaction is going to reach equilibrium when the A concentration reaches this value. We'll never really get there in our steady state non-equilibrium conditions, but it's convenient to write the rate law and redefine your variables in terms of that equilibrium amount, specifically in terms of a deviation from that equilibrium. So what we're going to do is change variables. In the numerator, you see the deviation from the equilibrium concentration. In the denominator, you see the deviation from equilibrium at the surface. The ratio of those two is going to be this new concentration variable, basically our dimensionless concentration variable y. Now if you put this into the reaction-diffusion equation and do the non-dimensionalization again, you get this expression. And this looks exactly like the one that we've solved before. Now, there's something I haven't shown you yet, and that's that you can define the Thiele modulus in a generalized way. Instead of defining it in terms of specific length scale in the problem, you can define it in terms of the ratio of the volume to surface area of the pellet. And this is not the surface area accounting for all the pores in the labyrinth of space inside the pellet. This is just thinking of that superficial surface area on the outside of the pellet. So 4 pi r squared, for example, if it's a sphere. And if you do that, then the length scale that you use to define your Thiele modulus is no longer r for a sphere, but r over 3. No longer r for a cylinder, but r over 2. And the slab case stays the same. For these three geometries, you find now that the definition of the Thiele modulus is very, very similar in all three cases, and it gives you results that all seem to kind of collapse onto the same universal plots. This was discovered by Eris. And what you see here is that they all go to 1 for small values of this generalized Thiele modulus, and then they drop. But now instead of being offset from each other, with one being 1 over phi and 2 over phi and another one 3 over phi, they all have this 1 over generalized Thiele modulus kind of behavior. So Eris used lambda, but now people usually will just decorate their phi somehow to indicate that it's this special one. Our next example, we're going to consider a single cylindrical pore. It's going to be a pore of radius r and depth L, and we're going to assume that r is much, much smaller than L. That's going to be important for justifying some of the assumptions of the model below. The catalyst sites are randomly dispersed at a density sigma along the surface, along the walls of the pore. So this is a little bit different than the slab geometry problem that we've been working, where the catalytic reactivity happens dispersed throughout the volume. In this case, the catalytic reactivity is on the walls of a pore, and we're modeling the pore at the length scale of the pore. We should, if r is really much, much smaller than L, still be able to use some of this machinery, and we'll see how in this example. The reaction A goes to B is occurring with a rate in events per site per time, given by this R equals K Ca to the N. And Ca, of course, again, is the local concentration in the pore, which we expect to be declining as you move from L, the mouth of the pore, down to the back of the pore, which is sealed at Z equals 0. Here's Z equals 0 right there, and Z equals L is the pore mouth out there. The concentration at the pore mouth is fixed at Ca sub s, same kind of boundary condition that we've been working with before. And we have no flux through the back of the pore at Z equals 0. Now we're going to construct a balance equation for species A. And we're going to have an accumulation term, a flow in term, a flow out term, and reaction terms. But we're doing this for a differential small z to z plus delta z slice. The pore was from 0 to L in depth, but we're writing a balance equation just on z to z plus delta z. If we wanted to really do this precisely, we might construct a balance equation that considers both r and z coordinates, the axial and radial components of diffusion and transport along the pore, with the reaction happening as a boundary condition at the surface at the walls at r equals r. What we're going to do is assume that since r is very small, and the same diffusivity is carrying things to the walls that carries them down the much longer length of the pore, that we can get away with ignoring concentration gradients in the radial direction and treating only concentration gradients in the axial direction. So that's where this balance equation comes from. We have a volume pi r squared delta z, and it's accumulating species A at a rate given by that volume multiplied by the derivative of the concentration with respect to time in that region. Then we have a flow it's going to be really a flow into that region at z plus delta z. There's the cross-sectional area, the diffusivity, and a dCA dz. So if the concentration gradient is positive as drawn, remember in the diagram that the z-axis goes this way. So if the concentration gradient is positive as drawn, then that is flow of species A into the volume element. And so there's no negative sign here. The flow out term, we have concentration gradient at location z multiplied by the diffusivity of species A and a pi r squared. Note that my diffusivities now are not effective diffusivities. They're the diffusivity of A in the fluid that occupies the pore. There is no tortuosity, no void fraction, because we're really modeling the actual diffusion process down this pore with no obstructions. The key thing that is added to this analysis that you wouldn't normally see in a standard diffusion analysis is that there is species A being consumed in each disk of the pore volume. We have an edge of that disk, and that edge has some catalytic sites at density sigma. It has a rate given by K times the local concentration of species A, and then there's a surface area that we have to multiply by to get the number of sites that are in that little wedge. So that's going to be 2 pi r multiplied by the delta z. So this is our balance equation, a little bit different from the ones that we've been looking at, but the same principles are really in here. We just have to remember that now when we go through and non-dimensionalize, that phi will have somewhat of a different interpretation. Okay, so we take the usual steps here. We divide by pi r squared delta z and take the limit as delta z goes to 0, and that gives us this differential equation, this partial differential equation. So this is the full transient description. If I start out with a pore that doesn't have any A in it, I could possibly predict how long it will take for that pore to be infused with species A and reach steady state in its reaction diffusion process. But most of the time we just care about that steady state reaction diffusion process itself. So we're going to go ahead and cross off that accumulation term and get a 0 over here on the left. We're also going to non-dimensionalize by the length of our pore, and we're going to non-dimensionalize concentration by the surface concentration. And lo and behold, what comes out? The same kind of equation that we've been solving. So our boundary conditions are going to be c equals 1 when xi is equal to 1, and the derivative of c is going to 0 when xi is equal to 0. So that was our no flux and our... Okay, the notes arrive at this equation, and it's a little bit different from the other ones that we've seen in another way, and that's that you have a general reaction order here that doesn't have to be 1, doesn't even have to be 0. You know, the notes go through and solve a couple of those cases. I want to focus on the case where n is equal to 1. That results in a linear equation. Also, you'll notice that the case n equals 0 results in a linear equation, but it's inhomogeneous, and the solutions are completely different from what we've seen. We'll probably have a homework problem about that case. If I use the case where n is equal to 1, then my equation reduces to this. I've got 0 equals the second derivative of c with minus this ratio, 2L squared sigma k over dA times R. And then I've got my factor of my dimensionless concentration sitting there. So we look at this equation and recognize that There's a new definition of the Thiele modulus for this specific problem sitting here, and that's that it should be the square root of this ratio 2L squared sigma k over dAr. Notice that there's a radius of the pore involved in defining this Thiele modulus now. So we have not just one length scale L in the problem, but also now another length scale has appeared. And then there's a factor of sigma that's accounting for the density of active sites on our pore walls. We don't have to resolve this equation. We've already seen solutions to this. We know that the solution ends up giving us a sine hyperbolic form, and then if we use that to formulate an effectiveness factor, we're going to get a 1 over phi tangent hyperbolic of phi. And if we're asked what is the rate in a pore like this, with a sealed end and catalyst sites dispersed along the wall of a cylinder and a pore mouth with a concentration of A fixed, then we know that we could just write down what would be the rate in that same pore if it was uniformly exposed to the concentration at the pore mouth, which would be the wall area of the pore, 2 pi r times L, multiplied by the density of active sites on the wall. So now I've got the number of active sites, and each one is consuming species A at this rate, Kca sub s. And of course, in reality, there's some depletion of the concentration as you move deeper and deeper into the pore, and that's what's accounted for in this effectiveness factor term, which includes everything that we've just gone through and done the derivation for. So the strategy in doing this is to formulate the model, do the non-dimensionalization, see the similarity to the cases that you've solved before, and you can really stop there. Most of these problems are going to be things that are tabulated solutions, often represented by a slab, cylinder, or sphere geometry, and then you just find the appropriate dimensionless parameter, and you can use solutions that other people have obtained in the past.